So then let's start. Welcome to seminar today. Talk is given by Dilip, who you all know, and he's going to speak about higher order time sharing masking. Yes.
Okay, so still not published yet. It's under review, and it's also an extension to the work that we submitted for the previous years. So initially you'll see some slides which are repetition, but I need that to, because it's an extension. Okay, so just start with some basics. So one way of masking is to do gate level masking, where you just take a netlist, which is an unprotected netlist with AND and XOR gates, and then you replace every gate with a masked version of it. There's a different way of doing it, which is algorithmic level, and that's what the TI people do. But yeah, that's not related to this work. Anyway, so the XOR is fairly straightforward. You can just operate on separate shares, but AND is a bit more complicated because you need all the shares to get the proper output. One of the early works, which was for gate level masking on hardware, is the DOM interrupt gate, which is also the cheapest one as of now. So it has a latency of 1, and you need registers to prevent glitches, and also it doesn't satisfy some composability properties, which is like SNI and Piney. So if you want to build a circuit and you use this gate, it's going to take some work because you want to be careful with how you compose these gates to get a secure circuit. And because of that, in recent years, there has been a few security notions which have become popular, which like the Piney one. So, but they always come with some extra costs. Like if you have a Piney AND gate, which is like the HPC2 gate over there, which is Piney, you can compose them however you want. You are guaranteed to get a secure circuit. But you always pay a small cost, a small or large cost, like a latency increase, or for HPC3, I think, you increase the randomness, and generally it's more costlier in terms of area. So. I will get there, but it's like yeah, I'll get there eventually. Yeah. Now, let's say I build a circuit with these AND gates. There is a drawback latency-wise because, like, the bigger the circuit is, the more the depth is going to be, and every AND gate introduces a register layer, so your latency is going to increase proportionally. So, in previous years, like 10 years ago, the main focus was on reducing area and randomness for a circuit. That was the main criteria for research. But recently, there is some work, or there is more popularity among low latency techniques. But usually, it's very inefficient in terms of randomness and area. So they sacrifice one thing to gain another thing. GLM is, the author is the same as the DOM author, and you take a DOM multiplier, you skip compression, so you just let it grow. The number of shares grow exponentially after every AND gate, and then you compress in the very end. So a drawback of that is that you end up with very high randomness and also very high area. And then GHPC it's Piney, which is an advantage over GLM, but it also has high area and randomness because it takes a function and then you evaluate the function based on just one share of the input, and then you use the other input as a multiplexer to select. You evaluate based on all combinations of one share, and you use the second share to select what you want. So yeah, it's also inefficient. And another drawback is that most of them only provide first order security. It doesn't extend to higher orders. There is, however, one exception, which is LMDPL, and it is very efficient. It has low area, randomness, and also latency, and it's also more efficient than the work we've published before. So the work that we published before in chess was was a masking technique which takes one cycle for any function. It could be as small as an AND gate or big like an ASS box. It's always one cycle. And we also prove that whatever circuit that you get from by using our masking technique is also composable secure. In the paper we say it's Piney, but it's also Piney and SNI. We use that property in this paper, so it becomes important later on. I'll also explain what it means later. So the construction works as follows. So you have one register layer, and before that register layer, you operate on share 0. You use some random bits to split it into multiple parts, and then you use share 1 after the registers to combine it with the previous computation to get 2 shares of the output. I'll use a small AND gate to explain how it works, and I also use this AND gate again for second order, for the future work. So let's say you have 2 inputs, x and y, shared as x0 x1 and y0 y1. So yeah, the straightforward way of multiplying it is just compute all cross products. But this is insecure because you have glitches. So the first thing we do for our masking scheme is to have some randomness and split the first share of x and y, which is x0 and y0. You use 3 random bits, and then you split them into 2 parts using 3 random bits. And then now you have 2 equations, which is the outputs, 2 shares, but it's still not secure because you still have glitches. So we add some registers in between to stop glitch propagation. Now it's secure. And a final addition is to refresh the inputs. And this is what gives the AND gate and also the masking technique Piney and SNI properties. So these were some results from the previous work. You have TSM at the top, which is ours, and LMDPL is of course more efficient. It's a lot smaller in terms of area and randomness, and all of them have latency 1. But our work is more efficient than in terms of area and also randomness when you compare it with GLM and GHPC. Now moving on. So there are 2 main contributions for this work. So the first one is that we extend the security. So we extend our technique to higher order security. And then once we do that, we also increase the area and randomness usage with that. So to counter that, we propose a trade-off, which is like we increase it works on the previous idea, and then we get a new construction which also reduces the area and randomness. So I'll first explain the first part, and then in the later half of the presentation, I'll go to the second part. So this is how it works, overall, like a basic idea. So instead of 2 cycles, now you have, let's say, D plus 1 shares. So every share is processed in a different cycle. So you process 1 share per cycle, and then they are all separated by register stages. It has the same advantage as of TSM, like the latency doesn't depend on the number of inputs or on the algebraic degree, so it only depends on the security order. So if you have a second order secure circuit, then it's like 3 cycles or 2 register stages, and the latency of 2. Then third order is 3, fourth order is 4, and so on. So now again, I'll use an AND gate, which is a very simple example, but it's easy to understand it this way. So it's split into 3 phases. Each input is split into 3 shares because it's second order. And then you have 3 phases, 2 register stages. So in the first phase, you only operate on 1 share, which is x0 and y0. And then in the next phase, you include x1 and y1. So you partially compute the products as you go on. And then finally, you include x2 and y2 to get the final results as 3 shares. So the first 2 phases are identical to what I showed before. It's the exact same, except now there are 3 outputs instead of 1. So you have x0, x1, x0 plus x1, y0 plus y1, and those 2 multiplied. And these are split into 2 shares each. So the idea is to, in the third stage, third phase, the idea is to use these 3 outputs from the previous 2 stages. And then you have the final share, which is x2 and y2, and then you multiply with them to get the final output. But again, these three outputs from phase 1 and phase 2 are shared, so it should be fine. So here's how it looks for the first two phases, and then the next step is to use some randomness, and then you have three outputs, and then you refresh the outputs, and then you store them. So you get two shares from this, and then you introduce a new share, which is just randomness. It doesn't work on the first two phases. And then the final part is to introduce the final share, which is registered, and yeah, it's delayed by 2 register layers. Maybe I don't show it here, but just so that it arrives at the same time. And then you compute the cross products, and then you you combine it with each share separately. So you have x2, y2, and x2 times y2. You combine it with the first share to get the output of the AND gate, first share output of the AND gate, and then you do it for the next share, and then the next share, and then you have 3 shares of the output. So this approach is recursive. Like once you have a first order secure circuit, you can get a second order secure circuit from it. And then from second, you can go to third to fourth. So the construction is also very, very similar for one order to another. So let's say you have an input which is X, which is a k-bit word, and then it's split into d+1 shares. Each bit is split into d+1 shares. And then you want to compute a function which is like a k input function, and then it provides L outputs, each shared. So the first step is to choose the first D inputs. You leave out one share from the end, which is XD, and then you take the first D inputs, and then you refresh them with some randomness. Again, it's for composable security, which I'll get to. And then you assume that you have something which is D-1 secure. You assume a circuit that you have a D-1 secure circuit, and then you just implement that using your first D shares. Next, it's very similar to the AND gate. So once you get the outputs of the circuit, you refresh them with some randomness. You introduce an additional share, you register it, and then finally you introduce the final share. And then you also delay them appropriately so that you get, like it's delayed like D cycles, I think. Yeah, D cycles. And then you compute some functions on the final share, and then you combine it with each share separately to get the output of the function. So these are the implementation costs, just to get an idea of how it scales. The latency is fixed with the order. It doesn't depend on the algebraic degree and nor on the actual number of inputs. But the area and randomness is a function of both the degree and also the number of inputs. And more importantly, it scales exponentially with the number of inputs. This will become important in the later half of the presentation because, yeah, this is the optimization that I'll do. Now, there aren't many low latency AES boxes. The only one that I could find is from GLM, and it has 2 cycles latency. Because there has not been much research on this. So the area is approximately half, depending on what compiler option I use. And then the randomness is 1/6 of it. So now I'll get to the part where I explain what these things are. So building a mask circuit, so all we care about is probing security, finally. But getting there is not very easy. It's not straightforward. So what people did first was to come up with some notions for gadgets, and then you compose these, you put them together to get a circuit which is finally probing secure. And these are the last 3 notions, which is NI, SNI, PINI. NI is not really composition related, but SNI and PINI is very popular. NI and SNI, it's you still have some constraints. You can't just put them together and expect it to be probing security. It could be a problem if you don't refresh some intermediate values. But PINI, it's a lot less restrictive. So once you have a bunch of PINI gadgets, and linear XORs is also PINI, but linear things are not SNI. so which is a problem for SNI. So once you have a bunch of Piney gadgets, and then you can just put them together, make a circuit, and you're guaranteed to get a circuit that's probing secure. Luckily for us, our masking technique is all. It's NI, SNI, and Piney, so we don't have to worry about composition at all. So one drawback with the increasing number of inputs is that, as I said before, it scales exponentially with the number of inputs. So let's say I have two examples, which is a Prince S box with 4 inputs and an AES S box with 8 inputs. So from 4 to 8, the increase in area is like 31 times, and the increase in randomness is 14 times, which is quite large. So in this paper, we propose a trade-off where we say we increase the latency by 1 cycle, but then we decrease the area and also the randomness from it. So this is how it works. Let's say I have a function, a k input function, and then I first implement it with a HOTSM block, one block, which is a huge block. Instead of doing this, I could split them into 2 halves of k by 2 inputs. Now it's like a smaller box which occupy less area and also less randomness. And then I need an additional stage after this to combine these two outputs of these 2 blocks to get the output. So for this, we use a DOM-like construction, which is because it's cheaper and it's not as secure as the HOTSM blocks, but it's fine. I'll explain it later. So security-wise, yeah. As a result of doing this, I have a big decrease in area and randomness, but the latency increases by 1, which is the sacrifice that we make. So security-wise, these 2 blocks at the left, it satisfies all properties, NI, SNI, Piney, and this is useful because, let's say, I have a DOM-based multiplier next, which is only NI and not SNI and Piney. Composing this is still fine. Let's say our block, HOTSM block, was just Piney and not SNI, then it would be a problem to compose this, but because it's both Piney and SNI, it's fine. And as a result of doing this, you get a bigger gadget which satisfies all properties, which is NI, SNI, and Piney. So yeah, to check how much the improvement is, we implement AES box, which is first and second order AES boxes with this optimization. I'll just quickly go through the AES box because it will become important later. So we have 8 inputs, A, B, C, D, E, F, G, H, and then 8 outputs. And then each equation can be represented in an algebraic normal form, which is like terms summed together. And they contain almost all possible combinations of the inputs, which is like 2 power 8, 256 combinations, and they have everything almost, these equations. So for the first order AES box, the first step is that I take the inputs and then I divide them into 2 sets, which is, yeah. The first set is ABCD, ABCD, and then EFGH, again, both are in 2 shares. And then I do TSM on both blocks separately. And then the output of this is all product terms of ABCD and EFGH separately, which is 2 power 4, which is around 16, minus 1. So we have 15 outputs. Now, so how do I get a term which is present in both sets? So I go through each term in the ANF form of the equations, and then I multiply these 2 outputs. So let's say I have ABCD, EGH. So I have ABCD from the first block, and then EGH from the second block. I can just cross multiply, which looks very similar to DOM. And then I do it for every term, DFGH. So I have D from the first set, and then FGH from the second set. I can multiply them. And then I have EFG. I don't have to multiply this because it's just present in one of these sets. So I can just use them as it is. Yeah. So for each coordinate function, I split them into domains. So you have 8 coordinate functions, and then each of them are split into 4 domains. And then for each of these equations, I go term by term, and then I add them to the domains, respective domains. So yeah, 4 terms, so I put them in 4 domains. And if there are just 2, then I just stick with 0, 0, and 1, 1. If it's just present in one of those 2 sets. And then I keep doing this for every single term. And once I finish, I refresh the 0, 1 and 1, 0 domains with a random bit. And you only need 1 random bit for this. And then I register it, and then I combine them to get the outputs. And this looks very similar to DOM, which is why I said it's a DOM-like construction. So as a result, we get something that's NI, SNI, and Piney. I was able to verify this with Silver, but yeah, it doesn't really accept any large circuits. So I can just make some 4 inputs circuits, like split 2, 2, and then combine them with a DOM gate, and I get all 3. So yeah, I couldn't verify the whole Xbox for this. So these are the implementation results, and this is not this paper, this is the previous paper, and just to make a comparison, I included those 2. So TSM, you have it in the middle, which is 14,000 and 20,000 depending on compiler option, and 262 bits. So the next is this work, which is TSM. Again, it's like 4 times smaller than the previous paper in terms of area, and the randomness is also a lot smaller. So when I compare it with the rest of the 2-cycle implementations, it's more efficient than in terms of randomness, but not TI, except TI. In terms of area, except LMDPL, which is always better. And yeah, it is what it is. And there are also some previous work which have more latency, but they are, of course, more efficient than our design, which is like 3 or 4 cycles. Now, we build a full AES with this. So we have an SBox, and then we instantiate 16 for the round function and 4 for the key schedule. And then it's all masked. Key schedule is masked, round functions are masked. And then so it's 10 rounds in total, so 2 cycles per round, and then you have 20 rounds in total. I know I said LMDPL has a smaller SBox, but the problem with that is it's based on dual rail, so you have to pre-charge it. So once you evaluate it, you have to reset it before you use it again. So what these people do is they have 2 instances, and then when one evaluates, the other resets, and then they just go between 2. So as a result, they need almost like two pairs of SBoxes for every SBox, which is why our design is smaller than LMDPL, but it also has more randomness. And then you have a design with TI, which has comparable area and no randomness, but also more cycles, 40 instead of 20. So for the second order secure AES box, it's very similar. There is almost no change, but the only change is that now you operate on 3 shares instead of 2. So again, you split them into two sets, A, B, C, D, E, F, G, H. Then you apply second order TSM on each set. You again get all the product terms of the first set and the second set. And then now you combine them, instead of 4 domains, now you have 9 domains, 3 times 3. Combine them, register them, and then you get the outputs. So the HOTSM blocks has a latency of 2 because it's second order, and then you need an additional cycle for the DOM thing, and then finally you have a latency of 3. So again, this is from the same paper, but it's without the optimization, which was the previous results. As you can see, the area and the randomness is quite large with latency 2. I couldn't find any other designs with latency 3 to compare with. So the area is again reduced by 4 times, I guess. And then randomness is also reduced by a lot, but it has an additional cycle of latency. And we also have some other designs which have higher latency, but also it's more efficient than our work. It's based on TI, HPC, DOM, yeah, etc. So now for formal verification, as I said before, Silver checks for almost all notions, probing, NI, SNI, and Piney, but it really cannot handle anything larger than very small circuits, like an AND gate or something. Especially if you are going to implement something in second or third order, it's not going to start unless you have something that's really small. So the first thing we did was to implement some AND gates, HOTSM AND gates for second and third order. And then we tested it. It passed all tests like Piney, SNI, NI, both in standard and robust probing modules. And then for the trade-off construction, where I increased the latency by 1, I used a 4-input Boolean function. Again, I split those into 2 parts, and then I use a DOM to combine them to get the output. I could check that for first and second order. Third order I couldn't, because it takes like days to complete it. Second and third order takes like 4 or 5 days to complete. Again, the trade-off construction also passes all the tests, NI, SNI, and Piney. Next, I was ProLead, which can handle larger circuits, but it cannot check all notions. It can only check for probing security. For that I could check both the first and second order AES boxes. It was fine, no leakage with I think 200 million simulations or something. And then finally I used mask verif. Again, this also handles larger circuits like the AES boxes that I have. It doesn't check for Piney, but it checks for the rest, probing, NI, and also SNI. Again, it's fine. The results were fine. It passed all the tests. Now for the larger designs, I used TVLA by implementing them on FPGA just to get to see whether it's fine when I implement it in the lab. So there are 3 designs for it. The first one is round-based AES-128, which is just the first order S box, the small one. And then there are 2 more, which is like 2-cycle AES box for the second order, and 3-cycle, which is with the optimization, where I increase the latency by 1 for second order. And I use 2 different boards for these because 2 of these 3 designs are quite large. So I use Sakura X for designs 1 and 2. And then for the third one, I use Sakura G because if it's really small and I try to implement it on a Sakura X, it's not going to show me anything. There's going to be a lot of noise. That's why I use a different board for it. So these are some univariate t-test results for first order secure AES-128. So the left figure is with PRNGs set to off, so there is no randomness in the circuit. And the initial inputs that I provide are unmasked. So they are not split into 2 shares. The top row is the power consumption that you see on the oscilloscope. And then the next 3 is like the first order, second order, and third order univariate t-test results. So for PRNGs off, there is no surprise. It leaks almost all the time for first order, second order, third order. For PRNGs set to on, there is no first order leakage as expected with 250 million traces. Second order, there is leakage because, of course, it's not second order secure. And third order, again, it's not. I don't see any leakage, but also don't have a proper explanation for it. Now for the second order secure AES boxes, again, it's the same thing. Top, I have the power consumption, and then first and second and third order statistic. So again, with PRNG set to off, I have leakage. Set to on, I don't see leakage in any of the orders, first or second or third. I do the same thing for the 3-cycle second order secure AES box. Again, with mask off, there is leakage. With mask off, I don't see any leakage in first or second or third. For the second order S box, I also do bivariate analysis. I don't downsample. I use the same number of points that I get from the oscilloscope. So the lower half of the triangle, which is to the bottom, is with PRNG set to off, and then the top half, which is towards the right, is set to on. So as you can see, with set to off, it exceeds 4.5. The threshold of 4.5 goes till 50 or 200, depending on the design. So yeah, this is also fine, security-wise. So in conclusion, we extend our masking technique from the previous paper to achieve higher order security, and most of the other work, I think existing work, the latency is always coupled with the algebraic deal of a function, but not for us. It only depends on the security order of the construction. And it's applicable to arbitrary Boolean functions and doesn't depend on the structure of the S-box or anything. You just need the equations. Once you have the S-box table, you can construct it from there. You don't need anything more than that. Yeah, finally, we prove, I haven't shown it in the presentation, but we prove in the paper that all our constructions are both Piney and SNR. And that's the end. Any questions?